In this video, we're going to start talking about quotient groups, which are analogs of the integers modulo n, but with z and nz replaced by other groups. Quotient groups are a fundamental construction in this subject because, like the integers modulo n, they tell us how bigger groups can be broken down into smaller pieces that can sometimes be used to give us non-trivial information about the original group. Before we talk about quotient groups, let's talk about quotient spaces. Remember that a group is a pair consisting of a set together with a binary operation satisfying certain properties. Well, quotient spaces are the underlying sets that we use to try to form quotient groups. But the issue, as you're going to see later in this video, is whether or not there's a natural way of turning these spaces into groups by making use of the original binary operation. So to define quotient spaces, let's suppose that G is a group and that H is any subgroup of G. You may remember from our proof of Lagrange's theorem that the collection of all left cosets of the group H in G forms a partition of the set G. In case you've forgotten the definition of left coset, remember that the left coset of a set H by an element G is the set of all multiples of the form little g times little h where H runs through H. And when we say that the collection of left cosets of a subgroup is a partition of the group, what we mean is that every element of the group G lies in one of these cosets, and that the collection of all distinct cosets is a pairwise disjoint set. Well, with this fact as a basis, we can define what's called the left quotient space of G modulo H, which we denote by G/H, to be the collection of all distinct left cosets of G modulo H. You might want to keep in mind here that even though I'm writing this as the set of all GHs where little g runs through G, many of these cosets could actually be the same. And since this is a set, I'm counting every distinct element only one time. Now, I also want to mention that all of what I'm talking about could also be done using right cosets to define what's called the right quotient space of G modulo H, which we would then denote as G/H with the H on the left here. But whether you start by defining the left quotient space or the right quotient space is partly a matter of convention. So when I talk about the quotient space in this video, I'm going to mean the left quotient space of left cosets of G modulo H. Let's introduce one more definition here before we move on. So given a group G and a subgroup H, we define the index of H and G, which we'll denote by absolute value G:(H), to be the cardinality of the collection of left cosets. Of course, this quantity could be infinite, but if it happens that G is a finite group, then again from our proof of Lagrange's theorem in a previous video, since the left cosets partition G, and since they all have the same cardinality, which is the cardinality of H, in the case when G is finite, we get that the index of H and G is equal to the cardinality of G divided by the cardinality of H. Now, as I've already mentioned, the left quotient of G modulo H is a potentially interesting algebraic object, which we hope might be able to tell us some important information about the algebraic structure of G. So, in order to explore this further, motivated largely by the example of the integers modulo n, we'd like to know whether there's a natural way to use the binary operation on G to turn the collection of left cosets of G modulo H into a group. Now, I could jump right in and tell you the answer here, but I think it may be better to first do a couple of exploratory examples to try to understand exactly what the issue is with trying to do this. First, let's look at the familiar example of the integers modulo n. So here we take our group G to be the group of integers under addition, and we let H be the subgroup nz for some natural number n. Using the definition, what are the left cosets of G modulo H? Well, in this case, they're precisely the collection of all sets of the form a plus nz, where a is an integer. But we saw in our video about equivalence relations that there are exactly n distinct cosets here, and they're represented by the integers from 0 up to n-1. So this is what we would now call the quotient space of z mod nz. Taking this one step further, in our video on integers modulo n, we saw that the rule a bar plus b bar equals a plus b bar is a well-defined binary operation on this collection of cosets, and that it turns this quotient space into a group, which is what we call the group of integers modulo n. Now, I'd like to remind you that the key fact in proving this was to show that this binary operation on cosets is well-defined, which here means that it doesn't depend on the choice of representatives for the cosets involved. That's something which we proved rigorously in our video on integers modulo n, and you could say it was the main ingredient in trying to turn this collection of cosets into a group in this way. Now let's see what happens if we try to mimic this construction with G equals the symmetric group of degree 3, and with H being the subgroup of S3 generated by the transposition 1, 2. So first of all, let's work out what the quotient space of G modulo H looks like. And in this case, because the index of H and G is 6 divided by 2, which is 3, we can just list out the three distinct left cosets of G mod H. So first of all, of course, there's H itself, which is the coset of the identity, and which you can also observe is the left coset represented by 1, 2. Well, to find another coset that I haven't discovered yet, I'll just pick an element that I haven't seen in any of the cosets that I've constructed so far, and I'll form the left coset with that element. That left coset is going to contain that element in it, and so it's certainly going to be a new coset. So, since I haven't seen the transposition 2, 3 in any of the cosets that I've constructed so far, I'll let my new coset H1 be the left coset 2, 3 times H. Well, in order to figure out what this is, I just go through and left multiply all of the elements of H by the transposition 2, 3. So first of all, I just have 2, 3 times the identity, which is just the transposition 2, 3. And then, to figure out what 2, 3 times 1, 2 is, I just do a little bit of scratch work. And after multiplying together these two permutations, I find that it's the 3-cycle 1, 3, 2. So the second coset in my list here is the left coset 2, 3 times H. And similar to what I mentioned before, you should recognize that this left coset can also be written as 1, 3, 2 times H. Well, now to find my final coset, I just choose any element that I haven't seen in my construction of the coset so far, and I left multiply it by H. So since I haven't seen the transposition 1, 3, I'll define the coset H2 to be 1, 3 times H, which I now work out is 1, 3, together with the element 1, 3 times 1, 2, which is the 3-cycle 1, 2, 3. Of course, this can also be written as the left coset 1, 2, 3 times H. And so now I've identified all of the cosets in the left quotient space of G modulo H. And the question is whether or not I can turn this into a group in a way analogous to the way that we turn the integers modulo n into a group. So what if I try to define multiplication of cosets in this quotient space by multiplying their representatives so that the left coset of H by G1 times the left coset of H by G2 is the left coset of H by G1, G2? Well, in case I haven't included enough literary devices in my exposition up to this point, I'll just go ahead and tell you that there's a problem, and the problem is that this rule is not well defined, because it turns out to depend on the choices of representatives for the cosets involved. So for example, we already mentioned that the coset that we called H0 can be written either as the identity times H, or as 1, 2 times H, and let's think about what happens when we try to multiply that by the coset H1 using this rule. Well, H1 is 2, 3 times H. So if I try to multiply together H0 times H1 using the representatives identity and 2, 3, I would get the coset 2, 3H, which is the coset that we called H1. However, if I try to multiply these two cosets together using the representatives 1, 2 and 2, 3, then I would get the coset 1, 2, 3 times H, which is the coset H2. But now H1 and H2 are not the same coset, so that shows that this is not a well-defined binary operation on this quotient space. Maybe this helps you appreciate a little bit why we were so careful when we showed that addition and multiplication modulo n are well-defined binary operations. Because here we see that in other groups, the analogous procedure of multiplying cosets doesn't always turn out to be well-defined. So now, of course, we'd like to know, when is multiplication of left cosets in this way a well-defined binary operation on the corresponding space of left cosets? Well, that brings us to the main theorem and the main definition in this video. The main theorem is that if G is any group and H is a subgroup, then multiplication of left cosets in the left quotient space of G modulo H by multiplying the corresponding representatives gives rise to a well-defined binary operation on the quotient space if and only if H is a normal subgroup of G. This is the main reason, as we indicated before, why normal subgroups of a group are important objects. Now, when the binary operation is well defined, it's not difficult to show that this binary operation turns the collection of left cosets into a group, and that group is called the quotient group of G modulo H. In order to let this sink in a little bit, I'd like to go through the details of the proof so that you can see why this is true and why normality is important in ensuring that this binary operation is well defined on the quotient space. For the proof of the first part of this theorem, let's call the rule here star, and let's suppose that that rule is a well-defined binary operation on the quotient space. Well, for this part, what we want to show is that for every element G and G, and for every element H and H, GH inverse is an element of H. That's precisely the statement that H is a normal subgroup of G. So in order to do this, first of all, observe that for any H and H, the left coset of the group H by the element little h is equal to H. And it's also equal to the left coset identity times H. This is just because if you left multiply H by any element of the group, you're just going to permute all of the elements of the group. Now for any element G in G, since I'm assuming that this binary operation is well defined, I have that the left coset HG inverse times H is equal to HH times G inverse H. And since HH is the identity times H, I can rewrite this as the identity times H times G inverse H. But that's then equal to the identity times G inverse H, which is G inverse H. And if you now think about what this means, it means in particular that the element HG inverse, which is HG inverse times the identity, must be an element of the left coset G inverse H. Well, that means that there's an H prime in H with the property that HG inverse is equal to G inverse times H prime. And now left multiplying both sides of this equation by G gives me that the conjugate of H by G is equal to H prime for some H prime in H. Well, now we've shown that for any G and G in H and H, GHG inverse is an element of H. So we've reached the desired conclusion that H is a normal subgroup of G. Next, for the reverse implication, let's suppose that H is a normal subgroup of G. And here what we want to prove is that this binary operation is well defined on the quotient space. In other words, what we want to prove is that if G1H is G1 prime H and G2H is G2 prime H, then when you multiply together these two cosets, the answer doesn't depend on the choice of representatives, so that G1 G2H is the same left coset as G1 prime G2 prime H. Well, in order to show this, first note that because each of the GIH's equals GI prime H, the elements GI prime are elements of the sets GIH. So each GI prime can be written as a GI times an HI for some HI in H. What we'd like to show here is that G1 prime times G2 prime can be written as G1 times G2 times an element of H. That will show that G1 prime G2 prime is an element of this left coset, but if the two left cosets intersect each other, then because the left cosets form a partition of the quotient space, they must actually be equal to each other. So in order to accomplish this, think about what happens when you multiply G1 prime and G2 prime together. G1 prime times G2 prime is G1H1 times G2H2. And now I can't just interchange the H1 and the G2 because this might be a non-abelian group. But one thing that I can do to get a G2 over here on the left is to insert a G2 times G2 inverse between the G1 and the H1. After I do that, if I regroup these terms, I can write this as G1 G2 times G2 inverse H1 G2 times H2. Well, now is where I want to use the assumption that H is a normal subgroup of G. The fact that H is a normal subgroup of G means that when I conjugate any element of H by an element of G, in this case conjugating H1 by G2 inverse, I'm always going to end up with an element of H. So since H is normal in G, it means that I can write this expression as G1 G2 times H prime times H2 for some H prime in H. But now, just using the fact that a product of two elements of H is another element of H, I have that G1 prime G2 prime is an element of the left coset of H by G1 G2. Well, as I've already mentioned, that means that the left coset of H by G1 G2 intersects the left coset of H by G1 prime G2 prime non-trivially, and since the cosets form a partition of the quotient space, that means that these two left cosets must be equal to each other. Well, that's exactly what I was trying to show, and it demonstrates that this rule is a well-defined binary operation on the left quotient space. Finally, let's check that when this binary operation is well defined, it turns the quotient space into a group. So remember, in order to do this, there are three things that we need to check. First of all, we need to check that this binary operation on the quotient space is associative. So for that, let's suppose that we have three cosets, G1H, G2H, and G3H in the left quotient space. And let's think about what happens when we multiply them by first multiplying G1H and G2H, and then multiplying the answer of that by G3H. Well, by the definition of the binary operation, the multiplication inside the left parentheses here is G1 G2 times H, and then when I multiply that by G3H, I get G1 times G2 times G3H. Well, now, just by using the associativity in the group G, I can rewrite G1 G2 G3 as G1 times G2 G3, and then unraveling the steps in the opposite order, I find that this left coset is equal to G1H times parentheses G2H G3H. Therefore, not surprisingly, the fact that this binary operation is well defined, together with the fact that the original binary operation on G was associative, implies that the binary operation on the quotient space is an associative operation. Next, to show the existence of an identity element in the quotient space, just note that for any coset GH in the quotient space, because of the fact that G is the identity times G is G times the identity, the product of the cosets identity H and GH and the product of the cosets GH times identity H are both equal to GH. Well, that's precisely the statement that the coset identity times H, which of course is just the same as H, is an identity element in the quotient space G mod H together with this binary operation. Similarly, for existence of inverses, if I have any coset GH and I multiply it by G inverse H, either from the right or from the left. Then, because G times G inverse is G inverse times G is the identity in G, the product of these cosets gives me the identity times H, which was the identity element in the quotient space. In other words, the inverse of any coset GH is just the left coset with representative G inverse. And now, since we've shown associativity, existence of identity, and existence of inverses, we conclude that when this binary operation is well defined on the quotient space, which is equivalent to saying that H is normal in G, the quotient space together with the binary operation forms a group. Now, I'd like to do a few good examples, but before we get to the meatier ones, let's try to tie up a few loose ends. So first of all, in our example number 2, we saw that when G is S3 and H is the subgroup generated by the transposition 1, 2, multiplication of left cosets was not a well-defined binary operation. Now, we demonstrated that already, but let's see if we can see why it's true in light of the theorem that we just proved. So just notice that if you conjugate the element 1, 2 of the group H by the element 1, 3 of G, then you get the element 2, 3, but 2, 3 is not an element of H. That implies right away that H is not a normal subgroup of G. And of course, this is consistent with what our theorem told us, that multiplication of cosets would be well defined if and only if the corresponding subgroup was a normal subgroup of the group G. Let's also go ahead and record a few basic facts that'll help us when we're working through our examples. So in these basic facts, let's assume that H is a normal subgroup of G, so that G mod H is a group. Well, we already saw in our proof of the theorem that the identity element in the quotient group is precisely the identity coset, which is H itself. We also saw that the inverse of any coset GH in the quotient group is the coset G inverse H. And we also used a couple times the fact that two cosets GH and G' H are equal to each other if and only if they intersect non-trivially, and in particular that happens if and only if G' is an element of the left coset GH. Also, it's not difficult to show using the definition of the binary operation in the quotient group that if you raise any coset GH to an integer power n, you're going to get the coset G to the n H. And finally, from this, it's not difficult to deduce that if you have any element little g in G which has finite order k in the group G, then the order of the coset GH in the quotient group G mod H must be a divisor of k. If you think about it, that's just because GH to the k is G to the k H, which is the identity element in the quotient group, and we've already proven that if a power of an element is the identity, then its order in that group must be a divisor of the power. So for the first example, let's take the group G to be C4 cross C4. And let's choose generators for each of the components to be X and Y, so that the elements of this group are precisely the collection of all ordered pairs of the form X to the I, Y to the J, where I and J here both run from 0 to 3. For a subgroup of G, let's choose the group H, generated by the elements X squared identity and identity Y squared. Now, one thing which I hope that you remember is that when you're working in an abelian group, every subgroup is normal. So in an abelian group, it always makes sense to talk about the quotient group of G modulo H. Let's try to understand in this example what the quotient group is. So first of all, since H is an abelian group which is generated by the set with two elements, I can write it as the collection of all elements of the form X squared identity to the I times identity Y squared to the J, where the I and J here run through all the integers. Since this is an abelian group and both of the generators here have order 2, I only really need to consider the exponents I and j equal to 0 or 1. So H is the group of order 4 consisting of the identity element x squared identity, identity y squared, and x squared x squared. Well, since the order of H is 4, it means that the index of H and G, which is the cardinality of G mod H, is the cardinality of G divided by the cardinality of H, which is 16 over 4, or 4. And since there are two groups of order 4 up to isomorphism, that tells us that the quotient group G mod H is either isomorphic to the cyclic group of order 4 or to the Klein 4 group. Now, in order to distinguish which of these two groups the quotient group is isomorphic to, let's recall some basic facts about these groups. If I write the cyclic group of order 4 as being generated by an element x, then it's easy to check that this group has one element of order 1, which is the identity element, one element of order 2, which is the element x squared, and that the remaining two elements both have order 4. On the other hand, if I write the Klein 4 group using generators A and B, so that it's the group identity A, B, and AB, then the identity element has order 1, but all of the other three elements of this group have order 2. So one way that I could try to distinguish between these two groups is by counting the number of elements of order 2 or of order 4. In order to do that, let's first of all work out what the four elements of this quotient group are. Remember that the elements of the quotient group are cosets of H by elements of G. And one element which I know is in there is the identity coset, which is just all of H itself. Now to find another coset in here which I haven't seen yet, I just pick any element in the group G which I haven't seen yet, and I form the left coset of H using that element. So for example, I haven't seen the element x, e yet in this list, so for my second coset in the quotient group, I can pick the coset xe times H, which I can work out is equal to the collection of elements that you see here. Now for the third coset, I need to pick another element which I haven't seen yet, and this time I'll pick the element identity, y, which gives me the coset that you see here. And finally, I need to pick another element that I haven't seen yet, and this time I'll pick xy, which gives me the coset xy times H, and that accounts for all of the elements of the group G mod H. Now, to try to understand the algebraic structure of the quotient group, let's first of all remark that because every element of the original group G has order dividing 4, we know that every element of the quotient group also has order dividing 4. So if I choose any non-identity element of the quotient group, it's going to have order 2 or 4. Well, if I now take the coset xe times H and I square it, using the rule for multiplication in the quotient group, this becomes x squared e times H. But since the element x squared e is an element of the identity coset, that means that this left coset is the identity coset in G mod H. So when I square the coset xeh in the quotient group, I get the identity, and that tells me that this element is an element of order 2 in the quotient group. Now similarly, if I square the element identity y times H squared, by a similar reasoning I get the identity coset. And finally, just to complete the calculation here, if I square the element xy times H, then I get x squared y squared H, and since x squared y squared is in the identity coset, this is also the identity coset. Well, now we've shown that every non-identity element in the quotient group has order 2, so that tells us that the quotient group is isomorphic to the Klein 4 group. For the next example, let's use the same group G, but this time let's let H be the subgroup generated by the element x, y cubed. As before, since G is abelian, H is a normal subgroup, so it makes sense to talk about the quotient group. And in this case, since H is generated by one element, we just need to consider powers of the generator. Well, it's pretty easy to figure out that this element is an element of order 4, so it generates a cyclic group of order 4, and these are the elements of the group. Okay, well, as before, if the order of the subgroup is 4, then it means that the index of H and G, which is the order of the quotient group, is also 4, so it means that the quotient group is isomorphic to C4 or V4. Now, I hope this doesn't end up being anticlimactic, but we'd like to go through and try to see which of these two possibilities it is. So first of all, just as before, let's go through and figure out what all the cosets in G mod H are. We know that the identity coset, which is just all of H, is in there. And if we pick any element which is not listed, we can find another coset. So we'll take xe times H, and it's pretty easy to work out what the elements of that coset are. Next, we pick another element that we haven't seen yet. So now we can pick xy times H, and we can compute what that coset is equal to. And finally, we pick another element that we haven't seen, so for example, xy squared, and that gives us the last coset in our list of cosets. By the way, you probably already figured this out, but when you're choosing these cosets, there are different representatives for each coset. So for example, at the second step here, if I decided to pick the element x squared y cubed instead of x identity, I would have ended up with the same coset. Okay, well, now let's try to say something about the algebraic structure of this group. In order to do that, let's first of all note that the element xe has order 4 in the group G, which by our basic facts means that the coset xeh has order dividing 4 in the quotient group. Well, if we compute the square of that coset, we get that it's equal to x squared e times h, and x squared e times h is the same as the coset xy times h, but the important thing is that it's not the identity in the quotient group. That means that the order of the coset xeh is not 2 in the quotient group, and it's definitely not 1 since it's not the identity element, so it has to have order 4. But if we have an element of order 4 in a group of order 4, then it's definitely a cyclic group. So we can conclude in this case that the quotient group is isomorphic to the cyclic group of order 4, and in fact that it's generated by the coset xe times h. For the next example, let's let n be an integer bigger than or equal to 2, and let's take G to be the symmetric group of degree n, and H to be the alternating group of degree n, consisting of the collection of all even permutations in Sn. This time, at least for n equals 3 or bigger, we're working in a non-abelian setting, and so before we try to talk about the quotient group of G modulo H, we need to give a reason why H is normal in G. Well, to see why H is normal in G, choose any G in G and H in H, and think about what happens when you conjugate H by G. Since H is in H is an even permutation, and whatever G happens to be, G and G inverse are either both odd or both even. We've mentioned this fact before. If you can write G as a product of transpositions, then you can write G inverse as the product of the same transpositions but written in the reverse order. That doesn't change the number of transpositions in the product. So if G is odd, then G inverse is odd, and if G is even, then G inverse is even. Well, if you have a product of 3 permutations, and 2 of them are both odd or both even, and the other one is even, then that product of permutations is an even permutation, which means that it's an element of the alternating group of degree n. But this is exactly the condition for normality, so it proves that the alternating group of degree n is always a normal subgroup of Sn. Next, for n bigger than or equal to 2, we know that the order of an is equal to the order of Sn divided by 2. So that tells us that the order of the quotient group Sn mod an is equal to the quotient of the orders of these two groups, which is 2. And of course, because there's only one group of order 2 up to isomorphism, that tells us that Sn mod an is isomorphic to a cyclic group of order 2. Now, we can even be more explicit about what this isomorphism looks like if we just write out what the cosets in this group are. So first of all, of course, there's the identity coset, and then there's also the coset 1, 2 times the alternating group. And to see that that is a new coset, you just need to observe that the transposition 1, 2 is not an element of an, because it's a product of one transposition. So that means that the coset 1, 2 times an is not the same as the identity coset. Well, if these are the two elements of this group, then of course the group is going to be generated by the non-identity element. So this shows explicitly that this group is a cyclic group of order 2. For our next example, let's let G be the quaternion group of order 8, and let's let H be the subgroup generated by the element -1, which is the subgroup of order 2 consisting of plus or minus 1. Now once again, G is a non-abelian group, so in order to make sure that G mod H really is a group, we need to make sure that H is a normal subgroup of G. Well, H is a normal subgroup of G in this case, and it's pretty easy to see from the fact that for any H and H and G and G, GH is equal to H times G. In other words, every element of the group H in this case commutes with every other element of the quaternion group. And so, when I take this equation and I multiply it by G inverse, I get that the conjugate of H by G is equal to H. Now that's obviously an element of H, and that's precisely what we needed to show in order to verify that this is a normal subgroup. That guarantees that the quotient of G mod H is a group, and the order of that group, which is the index of H and G, in this case is equal to 8 divided by 2, or 4. So since there are two groups of order 4 up to isomorphism, we know that G mod H is isomorphic to C4 or V4. Well, in order to tell which of these two possibilities it is, first of all, let's list out the cosets of G mod H. There's the identity coset, which is the set consisting of the elements plus or minus 1. There's the coset containing I, which is the coset containing plus or minus I, the coset containing J, and the coset containing K. Now, if you square any of the cosets IH, JH, or KH, you're just going to get I squared H, J squared H, or K squared H. So in all three cases, you're going to get the coset -1 times H. But since -1 is an element of H, that's just the identity coset in the quotient group. That shows that all three of these cosets have order 2 in the quotient group, so it means that the quotient group in this case is isomorphic to the Klein 4 group. For our final example, let's take G to be the symmetric group of degree 4, and let's let H be the subgroup of G generated by the two permutations that you see here. Now first of all, the key to understanding this group H is to notice that number 1, both of these permutations are elements of order 2, since they're each a product of two disjoint 2 cycles. And number 2, when I multiply these two elements together, first of all multiplying them as 1, 2, 3, 4 times 1, 3, 2, 4, that I get a product of two transpositions 1, 4, and 2, 3. However, if I multiply these two generators in the opposite order, multiplying them as 1, 3, 2, 4 times 1, 2, 3, 4, I end up with the same result. So that means that these two generators for H are two elements of order 2 which commute with each other, and therefore, thinking back to the presentation of the Klein 4 group, I have that H is isomorphic to the Klein 4 group, and that the four elements are the identity, each of the two generators, and their product. Next, before I can talk about the quotient group of G modulo H, I first of all need to check and make sure that H is a normal subgroup of G. And at first that seems like a pain because S4 has 24 elements, and H has 4 elements, so it seems like there are a lot of things to check. However, recall that in our video about normal subgroups, we proved that whenever you have a finite group G together with some generating set and a subgroup H together with a generating set, then to check whether or not H is a normal subgroup of G, you just need to check whether or not every generator in the generating set for H conjugates by every element in the generating set for G to an element of H. In this case, there are 2 generators for H and 2 generators for G, so there are 4 different things that we need to check here, but it's not difficult to go through this calculation and check that the conjugates of all of the generators of H by the generators for G lie in H. Therefore, H is a normal subgroup of G. Next, since the index of H in G is equal to the cardinality of G divided by the cardinality of H, which is 4 factorial over 4, or 6, we know that G mod H is a group of order 6. But up to isomorphism, there are only 2 groups of order 6, so this tells us that G mod H is either isomorphic to the cyclic group of order 6 or to the symmetric group of degree 3. In order to distinguish between these 2 possibilities in this case, we can first of all note that when we multiply together the 2 cosets 1, 2, 3H times 1, 2H, using the rule for multiplication of cosets in the quotient group, we get 1, 2, 3 times 1, 2H, which turns out to be 1, 3H, which is exactly the coset that you see here. Now, on the other hand, if we multiply together these 2 cosets in the opposite order, as 1, 2H times 1, 2, 3H, then we instead get that it's equal to 2, 3H. But notice that the transposition 2, 3 is not an element of the coset from our first calculation. So that means that these 2 cosets don't commute with each other. Well, the fact that we now know that G mod H is a non-abelian group tells us that it can't be a cyclic group of order 6, so it must be isomorphic to the symmetric group of degree 3. Now, there are lots more interesting examples, but if you understand these ones that I've shown you, then that should help you to navigate most of the ones that you're going to see later. That's the end of this video. Thank you for watching. In the next video, we're going to talk about the first isomorphism theorem for groups.